Now I'm going to find out the magnetic field due to bar magnet. The first point you consider at any point on the axis, that is called at any axial point. Suppose we have this is a bar magnet. This is a bar. Suppose this is a bar magnet. Okay, and this side is south pole and this side is north pole, and this bar magnet have a length 2L, say 2L. Okay, so magnetic moment is M is nothing but pole strength into separation, and its unit, as I told you in my first video, this is ampere into meter square. And now this magnetic dipole moment is a vector quantity and it is directed from south to north pole. Okay, now suppose we have to find out the magnetic field due to this dipole at any axial point, say point P, at a distance say r from the center of the dipole. Okay, now to find the magnetic field at this point, we have to place a magnetic north pole of unit pole strength. Okay, just like electric dipole. Okay, we have to place at that point where we have to find out the electric field unit electric positive charge. Okay, similarly here we have to place a magnetic north pole of pole strength unity, then find out the force acting on this unit magnetic north pole due to this north and south pole. Okay, for this north pole the force is acting outward because this is north pole of unity, this is north pole and north pole repel each other, so this unit pole strength of north pole in character repel force in the outward direction, so this is F1, and F1 is the force acting on that pole due to this magnetic north pole is mu 0 by 4 pi, this is for constant, into pole strength of this pole into pole strength of this arbitrary pole into, that means this is a concept. We have to consider unit north pole, so m into 1, and this distance np square. What is np square? Np square, what is np? This is a c, so cp is r, okay, cp is r, and cn, or say this is on is l, because ns is 2l, so on is l. So what is np? So np is nothing but r minus l. Okay, so this is your mu 0 by 4 pi m by np square. Np is r minus l whole square. This is your F1, force on the pole, force at this point on unit north pole outward. Similarly, force on that unit north pole due to the south pole is south pole and north pole attract each other, that means south pole apply force inward. This is F2, so F2 is the force on the point P due to S pole. This is attractive in nature, so F2 is nothing but again mu 0 by 4 pi, this is for constant, pole strength of the south pole m into the pole strength considered over here is 1 by distance sp square. Now sp is nothing but op plus os, so this is r and this is only l, so this is r plus l tar whole square, so mu 0 by 4 pi m divided by r plus l tar whole square. Okay, now the resultant force acting over P is F1 is outward, F2 is inward, but in F1 your denominator is r minus l, but in F2 your denominator is r plus l. that means F1 is greater than F2, therefore resultant force is F is nothing but F1 minus F2, and that is equal to mu 0 by 4 pi into m by r minus l tar whole square minus m by r plus l tar whole square. Mu 0 is taking common outside. Okay, this resultant force is actually called the magnetic field at the point P, because this is actually the force on unit charge. So force on unit charge is nothing but field. Okay, so B is nothing but mu 0 by 4 pi. Okay, m, the first term is r plus l whole square minus r minus l whole square, and your denominator is r plus l whole square into r minus l whole square. If you do the calculations, okay, it would be mu 0 by 4 pi, mu 0 by 4 pi. Okay, so this is this is what, this is m into, this is a plus b whole square minus a minus b whole square is nothing but 4ab, and your denominator is r square minus l square, because this is a plus b into a minus b whole square is whole square. So this is all about your calculations. So this is mu 0 by 4 pi m into 2l into 2r by r square minus l square whole square. This is your magnetic moment. So you have expression mu 0 by 4 pi, and this is m, so 2m r by r square minus l square whole square. M into 2l is nothing but magnetic dipole moment of the bar magnet. Okay, now if r is very greater than l, that is the distance is very higher in range than the magnetic length, then r square minus l square, you can say, is nearly equal to r square. So r square minus l square whole square is nearly equal to r to the 4. So this expression then becomes mu 0 by 4 pi. Okay, so this is 2m r by r to the power 4, r cancel, so mu 0 by 4 pi, and your expression is 2m by r cube. This is a magnetic field at axial point due to magnetic dipole at resistance r from the center of the dipole. Okay, and m is the magnetic moment. Okay, its unit is Tesla. Okay, so this is all about the magnetic field at axial point. You can also calculate the magnetic field. Okay, if you consider, suppose this is your bar magnet, again this is S, this is N, this is your origin, this is your separation. Suppose the point is now exist or situated over here, that is called the point on the perpendicular bisector of the magnetic dipole at a distance r, then find the magnetic field at the point P. Okay, so similarly as you have done in your electric dipole, same calculations over here, and your result would be B is equal to mu 0 by 4 pi m by r cube, if you consider r is very greater than L. Okay, under this condition your formula become this type, mu 0 by 4 pi m by r cube, and your direction of the magnetic field, okay, just similar as your electric dipole, opposite to the magnetic dipole. Okay, so magnetic dipole moment vector is from S to N, so your magnetic vector means magnetic field strength directed from opposite to M vector. So this is your magnetic field strength. Okay, so what we have studied till now, we have derived some magnetic field at some given point due to bar magnet. So first our point is on the axis of the bar magnet. So suppose this is our bar magnet ASN, each pole have a pole strength m, separation 2l, so they form a magnetic dipole, and the dipole moment m is m into 2l, that is unit is ampere meter square. So next we are going to find the field on the at any point on the axis of this dipole, that is this line, along this line, say at a point P, which is a distance r from the center. Okay, so for this we are place over this point P unit north pole, so that north pole repel each other. So on this unit north pole exert a force F1 mu0 by 4 pi this pole into this pole by distance square. This is the formula. Okay, just like Coulomb's law of electrostatics. So F1 is mu0 by 4 pi m into that NP is nothing but this is R, and this is ON is L, OS is L, so total is 2L, so this is L, and from O to P this is R, so from N to P this is R minus L, so this is R minus L, that whole square. So similarly the force on the point P due to S pole is nothing but mu0 4 pi m by SP square. SP is R plus L, that whole square. So since this is S and you consider a north pole, unit north pole, so this S pole attract this north pole towards the magnet. So F1 and F2 opposite to each other, and from this expression usually observe that in F1 you have a denominator R minus L, but in F2 you have denominator R plus L. So F1 is higher than F2, so resultant force is along F1. So resultant force is along F1, and that force F is equal to F1 minus F2. Just putting this value F1 and F2, we get the magnetic field, because this is the field force per unit pole strength. So mu0 by 4 pi, and you just doing the simple calculations, you have ultimately this expression. This is all about your expression m into 2l term into 2r. M into 2l is called magnetic dipole moment. So m 2r by r square minus s square the whole square. So 2mr by r square minus s square the whole square into mu0 by 4 pi. Okay, so under suppose you consider r is very greater than L, so r square minus L square is nearly equal to r square, because r is very greater than L. R is very greater than L, so r square minus L square is nearly equal to r square, so whole square is become r to the 4. Okay, so putting this value 2mr, this is r to the 4, 1r is cancelled out, so only mu0 by 4 pi 2m by r cube. So this is your magnetic field at the point P on the axial point, on the axis of the magnetic dipole, and this is mu0 by 4 pi 2m by r cube. Okay, and you can see that this magnetic field is along this side, and also your magnetic moment is along this side. That means your magnetic moment vector and your magnetic field are in the same direction if the point lies on the axis of the magnetic dipole. Okay, similarly you can easily prove, suppose this is your bar magnet, this is south pole, this is north pole, and the separation is 2l. Now the point T lies on the perpendicular bisector of this magnetic dipole at a distance r from the center of the magnetic dipole. Okay, so as we have studied, or we have done in electrostatics, the electric field on the perpendicular bisector, similar concept. So doing this okay, with that concept you can easily find out the magnetic field at that point is mu0 4 pi m by r cube, with certain consideration. What the consideration is, the distance is very greater than the separation between the poles. Okay, and one more thing, that magnetic field is opposite to the magnetic dipole vector. Okay, so this is all about magnetic field due to magnetic bar, due to bar magnet. Okay, we have derived the magnetic field at 2 points, one on the axial point, another and the magnetic perpendicular bisector of the magnetic dipole. Okay, in my next video I can compare a current loop with the bar magnet. Okay, I compare the current loop with the bar magnet. Okay.